When you go around, you will see a lot of ways how everything is done. A lot of time. Great, so pretty cool things you can learn about Aboriginal culture. So I'll just minimize that. So move that around. So timber is really old. So today I'm going to talk about timber skyscrapers, but they're not actually that modern. Tall timber buildings have been around literally for centuries. So there's an example of friend took when she went and visited, all made of timber, and there is a Chinese temple also all made of timber, and they're literally hundreds of years old, and they're still standing today. Okay, what do I do? There we go. But how do we actually get from a teeny tiny sapling to a full timber? That's what I'm going to take you through today really quickly. The first thing to understand about timber is it's a natural material, and it grows by photosynthesis like all plants. So it'll absorb carbon and then give off oxygen, and that happens during the day, and at night that's cycle reverses. But as a tree grows, there's a net carbon storage and a net oxygen release. And then at the end of life, what happens is all that carbon is released back into the atmosphere. And that makes sense, because otherwise forests and trees would constantly be depleting carbon, and then the balance in the air would shift, right? So forests themselves actually don't produce oxygen. They are in a stable state. Growing trees do produce oxygen though, and absorb carbon. So what we can do then as a way to mitigate climate change is that we use wood in buildings and lock away that carbon for you. Of taking extra carbon out of the atmosphere. And then that's to grow trees or carrots, whatever we eat. Basically, that's how we grow timber as a building material. Something in the chat, and I'm wondering if they're just trying to say they can't hear me. Oh, okay, I'll be really close. Sorry. I'll be really close to move that away and stare at that screen. Okay, I hope it's better now. Right, so that's the way how we can store some carbon. And because it's a material that just grows, so nature does it for us, there's also very little energy involved in actually extracting it. If we extract iron ore to make steel, or we build a quarry like we have at Mount Kuta to get the aggregate for concrete, that takes a lot of energy. Then it takes energy to process it. So making steel is very energy intensive, because you'd all know from your material classes that it has a high melting point, and to really get the temperature that you want takes a lot of energy. And you would also know from your concrete design that concrete itself, by making cement, emits a lot of carbon dioxide, right? So not only does timber not take a lot of carbon to make it as a construction material, it also then locks carbon away. So that's just a smart way of building. Okay, I've broken something again. And there are lots of different programs that also certify that and make sure that we don't, for example, cut down native bush or rainforest or those kind of things. And obviously there are different types of forests, right? So when I'm talking about timber engineering, I'm talking in plantation forest. You see a lot of them if you drive up the Bruce Highway past past Caboolture. So when you're driving towards Mooloolaba, there's a Glasshouse Mountains. There's a huge plantation of pine trees that we mostly use in timber structures. And then we have other types of forests, and they obviously have other purposes. So they will have biodiversity. That's where your koalas live in the gum trees, and other purposes, right? So that's something to keep in mind. So then how long does it take to grow a timber building? Any ideas? Yeah? They take 30 years before you can cut them, usually. Yeah. So how long do you think it'll take in Australia to grow enough wood to build this 10-story building in Melbourne? 5 years? 4 years? 40? Okay, so we can look at the amount of material that's in there. So we just take that from the BIM model. And I've summed up all the wood. It's about 1,000 cubic meters of wood in a 10-story apartment building. And it takes the Australian softwood plantations 1 hour and 15 minutes to grow the entire timber needed to build a 10-story building. It's pretty neat. No, it is like that. That's about how much timber we harvest. It's between all the plantations. So all the plantations together produce that much timber, 10,000 cubic meters of timber every hour and 15 minutes. Right? And then, of course, some parts of the plantation will be saplings, and they'll be growing into trees, and some of them are trees that are old enough to harvest, so they will be around 30 years old. The thing about timber that's really interesting, but also scares a lot of students, is that it is a natural material and it is not isotropic. It has 3 distinct directions, parallel to the grain. I should have brought a bundle of straws, but basically it's like drinking straws. Those are your timber fibers, they're hollow in the middle. So that's what we call the grain direction. And then directions perpendicular to that. And they're a lot weaker because you can imagine you can squish straws, right? And you can buckle them. But if you pull on them, and if you have a bundle of them and you push on them, you can actually stand on them. So the grain direction is something that's really, really important. And if you look at the table, this direction, the table here in the front, that, I mean, it's a veneer. It's made to look like solid timber, but it's not. But that would be the grain direction here in the front table. There we go. That's the straw analogy. So strong and stiff parallel to the grain, but pretty weak perpendicular to the grain. So that makes it just a little bit more interesting to design this timber and apply it to its strengths. And I've just put there material properties for you to just to sort of visualize that in comparison to steel. Obviously, timber is a very light material, but your timber beam will be much bigger than your steel beam. So both steel and timber are lightweight materials for light structures, but your timber members will be bigger than a steel section to support the same load. However, again, timber is also a lot lighter, so they might end up weighing about the same. Okay, I've talked about that. So most of you, if you live in an apartment building or a Queenslander in Brisbane, will have timber in your roof because we use it for roof trusses. And if you go to any park and you're having a barbecue, you'll probably see one of those shelters there, one of those shade structures. So that's ways how we apply timber in tension and in compression, the directions where it's really strong parallel to grain. In bending is a little bit more interesting as well because of that non-isotropic structure. And what happens in bending actually is that deep beams predominantly fail in, is it happening? They fail in shear. So that's something to keep in mind. It's a different failure than you would get from a steel or a concrete beam. I've mentioned that perpendicular to the grain, it's a lot weaker. So we also need to think about compression, but also about tension. And anybody who's split firewood would know that in one direction it's very easy to split. You can split it with your bare hand, actually. I don't know if any of you do any martial arts, but I did a workshop where we actually broke timber. You can do it between the grain. Don't try to do it the other way around, you'll break your hand. And then there are imperfections that we also have to deal with. And that's why we make engineered wood products, because every tree has branches and they introduce knots. And then there will be other things like drying cracks and maybe some, some holes from borer and whatnot. So that's why we try to make then an engineered product where we can control the properties a little bit more. And examples are glue lamp, laminated veneer lumber, and cross-laminated timber. And that last one has become really popular as an alternative to concrete slabs because it is made as really big slabs. They're about 4.5 meters wide and as long as 16 meters. And if you've biked around Kangaroo Point, probably a year ago or so, you would have seen a timber building with COT going up. And it's called Monterey. It's sort of, anyway, you can check it out. Look it up, Monterey, Kangaroo Point. It's a 10-story apartment building in Brisbane. I'll talk about it a little bit more. And then plywood, and most of you would have used plywood for some DIY projects. We can reinforce it by using screws and distribute those stresses a little bit better. And we can use really cool connectors that are plug and play to put members together really quickly on site. And we're also using some of them in Australia, and they were used in that building in Kangaroo Point. We use also a combination of timber and other materials, so hybrid structures. Sometimes we combine it with steel. We can do it with concrete. So basically the timber becomes the formwork for the concrete. And by making this bond, we have a really light beam, but then a good stiff concrete slab that's also good for acoustics and vibrations and those kind of things. And there's a student accommodation in Melbourne where they use those concrete composite floors. This is something that comes from the Cuzzies across the ditch. They've explored post-tension timber for seismic applications. In the corner there, that big wall structure, one of my friends, Justin Brown, did that while I was doing a PhD in New Zealand. He started a little bit after me, and he built that tall timber tower, which is post-tension, similar to post-tension concrete. You can imagine it's like a rubber band that goes through like a hollow part in the timber, and then you pre-stress it a little bit. And what happens if there's an earthquake? It self-centers. And that's pretty neat because most structures are actually structurally safe after an earthquake, but they have so much residual deformation that it's no longer usable. And you know that serviceability limit state is a failure if it's not met and the structure has failed. So most buildings are demolished after earthquakes because they failed serviceability limit state. Yeah, go back.
Yeah, the first time
Oh, it's 9 meters tall. Yes. So this thing, the strong wall, is 9 meters tall. No, higher than that. No, sorry, I should have said. Thanks for pointing that out, Lewis. So every floor is an actual story. That's how tall it is. That's how tall it is. I have a photo where they all sit on it. I should have used that one. Thanks for pointing that out, Lewis. But moving on to now the timber skyscrapers, right? That's why we're here. So we've got a couple in Australia where we are a bit generous with how we define a skyscraper. We say if it's 10 stories, we call it, right? But there are actual skyscrapers made of timber. They're 85 plus meters tall, and they'll have 20 stories or more. And it all started in the UK. That's because the first engineered timber was made in Europe. And yeah, so there are a couple of them in London. One of the biggest buildings is this big apartment block in London, which has just enormous floor space. But in Australia, I've showed before the Forte building. You can walk around it in Melbourne, 25 King Street. And so some of you have been inside the building, I'm assuming. What's that? I've put a video there for you to you know, if you're interested about the construction of it. And then Monterey Kangaroo Point, which is the luxury apartments. And we went on a site visit there in 2019, 2020. In Canada, this is one of the actual tall ones, 18 stories. That's student accommodation. It's got concrete cores. And in Europe, so they are really taking the cake. So the tallest one still to date is the Brumunddal in Norway, which is completely timber, no concrete, no steel beams, no cheating. It's all glulam and CLT. Oh, you wanted to take a photo of that one? Awesome. So so that's it for me. I've put links there, and I'm sure Martin can share the PDF slides. There's a TED talk which explains a little bit more how I started to talk about, you know, the environmental benefits. It's aging a little bit now. Michael Green did this talk, I think 10 years ago, and he's an award-winning architect in Canada. And he basically gave a TED talk on why he thinks we should be building timber skyscrapers. And there's also a video that sort of reviews some of the tallest timber buildings and showcases them a little bit. And now if you think, oh, I want to design with a material that is a little bit more complex than concrete and steel, and maybe I want to do something that's good for the environment and challenge myself, you can take Civil 4334, Design of Timber Structures. Thank you. And yeah, learn a little bit more about that. UQ has the only undergraduate timber course in all of Australia. So you'll be highly sought after because timber construction is booming in Australia, and we're the only ones teaching it in a pure dedicated timber course. So yeah, that's it for me. Over to Lewis.
In the 70s, so all these books. This one. Going to keep it short, guys. So I was thinking, what can I say after Lisa said everything about timber? That's not much for me to talk about. So I'm going to talk about myself because I'm an egocentric person. I was discussing this with Martin. What would be interesting for you guys from the timber point of view? Lisa talk about the good things of using timber things. And also this part of talking about myself is just to work here. And I have done a pretty long journey to be here. So this is my first slide. Which also has a smiley. Sorry. No, here. Yeah, okay, I will stand here. There's not much. If you ever have, I don't know if you have been in South America or not, but Uruguay is in South America, it's in the south of South America. It's only a 3 million people country, and we don't have much than soccer players and cows. We have actually the country in the world with more cows per person, which is 5, right? And if you ever have time and money to go to South America, don't waste your time going there unless. I mean, South America is beautiful, and we don't have much to offer. I think living there is pretty okay, but in terms of landscape, there's not much. That's my city there, next to the Atlantic Ocean, in front of Buenos Aires, which is a big city. Anyway, long story short, in 2003, I had my bachelor in chemistry. So I'm working in civil engineering, but I studied chemistry. And I felt it was not enough, so I did chemical engineering as well, and I finished that in 2005. And at that time, I was working. When I finished chemistry, I was working at the university, teaching mainly and doing some research. And I was progressing my career, I would say that it was kind of assistant lecturer. And then when I decided to have an academic career, I said, okay, I need to do a PhD, but not here. Let's go somewhere else. So I found a good position in Barcelona. So I moved to Barcelona in 2007, and I did my master and PhD in materials and in heterogeneous catalysis, basically materials to produce hydrogen from fuels. The whole idea was to ferment waste, produce alcohol, and with that alcohol and using the proper catalyst, produce hydrogen. Then one thing I learned from my PhD is that hydrogen is not the future, no matter what they say. I agree with Elon Musk that says that the electricity or electric cars are the future, not hydrogen. But anyway, this is a photo of me doing the PhD there in Barcelona, coming from an engineering, after doing chemical engineering. My background is more like related with chemical engineering rather than with chemistry. So it was a little bit tough for me to do this PhD, especially in inorganic chemistry. Barcelona is a beautiful city. I have one of the best times. I have a pretty good life as well now. I don't want to be unfair with my family, but it was a good time as well doing a PhD. And then I moved to Poland as well. And when I was writing my thesis, I went to Poland with my wife. That moment, my girlfriend, she was doing a master, so she had to come back to Poland. She was living with me in Barcelona. And then I lived 1 year there and experienced, being from Uruguay, we don't have snow, which is pretty much like Brisbane. And then I spent 1 winter in Poland, like -17, I remember, riding the bicycle in the snow. You probably get used to it, but not me. Also totally incredible experience. Well, so I have done pretty much a lot of things. Then when I was finishing my PhD, I found a position here as a postdoc. And I came here just 2 months after I finished my PhD to work in a project funded by the Bill and Melinda Gates Foundation to burn poop, I would say. I don't want to say shit because this is a public talk. So are we recording this? No. Yes. Probably you haven't heard about this, but actually this guy his wife, they put a lot of money into this, like billions of dollars from this foundation, and they were funded projects all around the world. We have a consortium here with UQ with other 2 universities in Canada. And actually my work, as I was working in gasification and combustion, basically they hired me to burn poop. We were doing this kind of reactors where we were mixing the poop with sand. And this was an exposition in India that we had in 2014. Then the toilet fair, and this is our cheap toilet. The idea was to fulfill one of the, actually 3 of the Millennium Goals, to eradicate malaria and the spread of diseases, especially from developing countries where they don't have access to sanitation, to develop a cheap toilet. Anyway, there was a lot of science involved in that, and that this is kind of wrap up. This is the end of my journey. I'm working now in timber, but I will explain you later. So what is my point with all this? Well, as you can see, I have done pretty much a lot of things. I have worked as a researcher. I'm working in timber now. I have published papers in energy, ecology, combustion, timber, education, pretty much a lot of things. So this is only, I like to think myself as a scientist rather than a researcher or a guy in a square that I'm doing civil engineering. There's too much there. This is linked with my next talk because you will see that has nothing to do with civil engineering, and at the same time has a lot to do. So the point is that timber research is a multidisciplinary area. Yeah, and otherwise I wouldn't be here. That's the point of this. So let's talk about durability related to timber engineering. Well, Lisa explained to you that timber It's a renewable material and it's good to use in buildings. It grows very fast and carbon storage, all that story, but we need the buildings to last or as much as possible. Which brings me to the when we were showing these photos of the buildings in what was Japan. That's all. I think they replaced some parts, right? Which leads me to the paradox of the Theseus ship. If you replace all the parts, is it still the same building? Apart from the philosophical question, can you say it was there for 1,000 years if you replace all the parts? It's a little bit like, eh. Anyway, basically, yeah, the problem with timber is there are two main problems, and this is where my research stands. Wood gets wet, as you can see in this picture, and the wood is food, right? Not for us, but for many organisms. Let's start with the problems of wood getting wet. Well, as you know, or you don't know, wood absorbs water from the environment. It can be in the form of liquid water from the rain. If you submerge a piece of wood into water, it will absorb water. Or if it's humid enough in the air, because the air we're breathing right now contains water, right? Dissolved in the air. That water will in the air will tend to be in equilibrium with the amount of water we have in the wood. That absorbing and desorbing the water creates that the wood swells and shrinks. And this shrinking and swelling will produce, if it's fast enough, will produce cracks in the wood, or also will produce the fasteners, which are important for timber because you cannot build a timber building without fasteners. You need to have plates, screws, nails, all these kind of things. All the fasteners will start to be loose because of this shrinking and swelling. Then imagine a nail will start to pop out. In addition to that, we have, as Lisa explained, that the anisotropy of timber means that it's different in different directions. This produces that this shrinking and swelling is different, is larger, for example, in the transversal direction. So it will not swell much in the longitudinal direction. It will swell and shrink more in one direction than the others. And this will produce deformations in the material. All this will induce stress, and the water present that in the wood that's coming from absorption of water will produce corrosion of the fasteners. The corrosion of the fasteners will produce metallic oxides. These metallic oxides in turn can affect the material, the wood itself, producing wood degradation. And all this mix of things will produce weak connections and, well, cracks and failures, but mainly weak connections and weak the connected elements in our buildings that we need to avoid. So this is one leg or one part of my research. We are running projects, several projects where actually Martin is doing one where we are studying how the impact of moisture content affects the nail connections. The second part of this is that, well, the second problem of wood is that wood is food for many animals, like this there. We have porcupines, rabbits. I can't remember the name of the first one, but I knew it. And termites, and that's why I have this insect in red there. And also fungi can eat wood. These animals or these organisms, they have enzymes in their organisms. These enzymes can degrade cellulose. We cannot do that, but it's pretty common for several mammals to do that in any case, I had never seen a rabbit eating no, but they can actually. I mean, a building, a timber building. I have never seen that. But termites, yes. Actually, I almost purchased a house that was infested with termites. So termites are a problem, especially here and in the United States, not in Europe. Luckily, you lucky bastards, you don't have termites there. I think it's too cold for them. But yeah, and these guys will produce a lot of holes in the wood that will lose density and integrity of the material. And also for the most problematic thing with fungi is that when you see that the timber or the wood is rot, it's too late. Because I don't know how much you remember from biology, but the fungi have like these three stages: the spores, then and then the filaments where you cannot see actually anything, and then the what you can actually see from the fungi, and that's too late. When you see the growth of the fungi, that's too late, and the process we are running are trying to assess the loss of performance, the mechanical loss of performance of the timber at the early stages. It's basically when we know there's fungi there, but we cannot see it because we're just putting it. And it's pretty much with we can have like a 50% loss in the mechanical strength, with only 5-6% loss in the mass. So which is pretty amazing. So yeah, these two problems, and these problems are interconnected also with the water, right? Because these, especially the fungi, they need water to grow. So wet moisture or wood getting wet has all the problems that I mentioned before, plus this. So if you have your wood dry, you will overcome the majority of these problems. Yeah, yeah. Actually, this is more for Lisa's side, but when you design or when you construct, you need to leave gaps for the water to dry from pieces of wood. Otherwise, but basically to avoid the growth of microorganisms. So well, I will talk about these two issues. So the best way to overcome, or I don't know if the best way, but one of the ways to overcome these problems is to treat wood. This is why we treat wood. There are two reasons. Because of the two problems I mentioned, to prevent water absorption, we can mechanically avoid the absorption of water into the wood, or the water to be in contact with the wood. There's also another possibility of applying heat to modify slightly the chemical composition of the wood, because the water, what does it mean that the water is absorbed in the wood? Well, the water will link chemically with the wood. What happens? The microstructure will include basically this of carbon with one OH group, like alcohol, and the molecule can be there. So basically, if you remove these OH groups from the cellulose, you're removing places where the water can be linked to the wood. And this is something that is commonly done in some places. We are also running some projects to do that. Basically, we apply heat, and by applying heat and not heat 200, 300 degrees, just 80, 100, 120, you can remove part of these groups and avoid to have a large water absorption. And the less water it absorbs, the less shrinking and swelling, and also the less growth of fungi.
Chemical composition of the material. Every step of the material is not only
Cheers for that. Don't drink water. Water kills, basically. Okay, so now I remember why I put this image there. It's because I wanted to show you that the OH group where the water can be linked. There's another way to do that, which is basically what is you insert chemical ramification there, and you eliminate the link, the site where the water can be linked to the wood. The second part of treatments are to avoid the guys that eat the wood, and it's mainly done with chemical products, like for example CCA or LOSP. One of the main problems with CCA, you may heard about that, is that chromium is not very nice for humans, so we try to avoid it. It's okay if it's going to be under the plasterboard or something like that, but it's started to be banned all around the world. One example is the playgrounds for kids. I think here they ban it and then they remove the ban. Are you aware of that? ACQ. Yeah, I didn't want to give more acronyms for them. The ACQ is another one, but I think they put the ban here following the US direction, and then they were having some impact in the economy, and they removed the ban again. Good. It's poison for the microorganisms and the animals, so it's poison for us as well. So it's not a good thing to have. Anyway, the development of new alternatives and the new chemical products is in progress in many parts of the world, but the problem is that there's not much sharing of the IP, of the the information, the intellectual property. So the advancements of that is very unknown. Anyway, why I'm saying this, because this is also adding another variable to our research. So which some of the questions we're trying to answer by doing research is how the water decreases the lifespan of the timber and the connections, especially, and how that loss of lifespan is related with the weather and the geographical conditions, because it's not the same if you are in Tasmania that you are in northern Queensland. Humidity of the air is important. Also, proximity to the salty water. The salty water, you may know, that's really, really bad for the metallic connectors. And for the wood, also the wood is affected by the, I haven't mentioned it because I haven't run any project, but the sunlight is also affecting the wood, not only from the aesthetic point of view, because it's changing the color, but also it's damaging the mechanical properties. So when we're in those places where you have a lot of exposition to the sun, the wood is more impacted. So as I was saying, with these chemical treatments are adding another variable. So one of the questions we're trying to answer here is are these chemical products affecting the loss of performance because of due to the water absorption and desorption, and what happens with the connections? So the connections are more corroded, less corroded with the chemical products. To what level of chemical products? High levels, low levels? What happens with the wood in terms of microscopically in the wood? What is happening with those linkages? Well, corrosion, I already mentioned corrosion. This is kind of a different discipline, so we're trying not to step much on there. Actually, I started with some project where I was studying corrosion, but now then more to use, like in Martin's project, stainless steel to avoid, at least at the level of we're going to study, steel, stainless steel is corroded. We're trying to minimize that problem. Another problem is that the chemical products, when they are when the wood is treated, can leach from the wood. From that leaching, if the wood gets wet and dry, wet and dry, wet and dry, with different cycles around the year, the treatment can be leached from the wood, and that will produce that the wood is not treated anymore. So there are some studies of studying how the link from the chemical product to the wood is done, and how can be enhanced in order to avoid leaching. Yeah, another question, how I have this last one, how bad is the fungal attack in terms of loss of mechanical performance? Yeah, basically the same, but for fungal attack. And what are the mechanisms, basically what is going on in the wood that it's producing the loss of mechanical performance, right? I think I'm talking too much here. So, and this is where our research stands. I don't have anything else to say. I don't know why I have Felix there, but